Hello, I am Reinaldo Francener and I will be talking about production of QED bound states in photon-induced processes. QED bound states are electromagnetic interactions between charged lepton and antilepton. These bound states are subdivided into para-states and warp states. Para-states are singlet states, that is, lepton and antilepton have antiparallel spins. These states decay into even number of photons, thus can be produced by fusion of an even number of photons. Warp states are triplet states, so lepton and antilepton have parallel spins and the bound state it has spin 1. This configuration decays into odd number of photons, being the minimum obviously 3. These states can be produced by fusion of an odd number of photons. In this work, we use the formalism of the equivalent photon approximation, which aims to replace the electromagnetic field of a charged particle by a flux of photons that is equivalent to this electromagnetic field. This equivalent photon flux is represented in equation 1. With the equivalent photon approximation, we can factorize the collision cross-section of two hadrons into photon-photon cross-section that give rise to QED singlet state multiplied by the photon flux of each hadron and integrated into the energy and photon space, as shown in the equation 2. With equation 2, we can easily obtain a rapidity distribution by exchange variables omega-1 and omega-2 for invariant mass and rapidity, as shown in equation 3. For triplet states, we can also use the equivalent photon approximation, as shown in equation 4, which uses the photon-hadron cross-section that gives rise to a warp states presented in equation 5. For the photon-photon cross-section that gives rise to a singlet states, we are using two distinct equations. The Low's formula, given by equation 7, which has invariant mass dependence via Dirac delta, and the Breit-Wigner's formula, which has dependence on invariant mass. The Breit-Wigner's formula has a behavior very similar to the Dirac delta. It has a peak in a central mass, but it falls very quickly with small deviation from the central mass, as shown in figure on the left. In the right figure, we present a rapidity distribution for the production of parapositronium by two photons in Liard-Liard collisions in LHC energy. We see that the use of the two cross-section leads to the sum distribution, so they are equivalent. Hadronic collisions that occur in colliders can be classified into three distinct groups: frontal collisions, peripheral collisions, and ultraperipheral collisions. This last class will be our interest in this work, because hadrons pass relatively distant from each other. Then the strong interaction is superseded and we can do a purely electromagnetic analysis of the collision, so that we can disregard the frontal and peripheral collisions. We use the absorptive correction of the step function. By collision geometry, when there is overlap of the hadrons, that is, when the impact parameter is smaller than the sum of the incident hadron's rays, the step function argument is negative and returns 0. On the other hand, when the impact parameter is greater than the sum of the rays of the incident hadrons, its argument is positive and then returns 1. We also use different nuclear form factors in our analysis. We focus on 3 distinct for heavy ions: point-like, monopoly, and realistic. The photon flux behavior for these 3 form factors applied to lead is shown in the figure. We see that the fluxes differ in regions very close and internal to the hadrons. Then, using these 3 different nuclear form factors, we obtain reasonably distinct results. This tells us that it is very important that we use the most accurate form factor, the realistic. In this figure, we show the rapidity distribution of the production of parapositronium in ultraperipheral collision of lead with LHC energy. The results are remarkably different due to differences in photon flux near the center of the hadrons. We also study spatial distribution for the cross-section of bound state production. We present here a comparison of the production region of different flavors of lepton bound states. We see that the production region is more extensive the smaller the mass of the produced leptons. This is because heavy lepton bound states require more energetic photons to produce them, and these photons are found more abundantly near the hadrons. We build distributions for hadronic collisions according to the energy of the RIC, LHC high luminosity, LHC high energy, and FCC. Here I present the rapidity distribution at the Born level for singlet states. In the first line, we have the distribution for heavy nuclear collisions. In the second line, for proton-lead collisions. And in the third line, for proton-proton collisions. We estimate the total cross-sections at the Born level in femtobar for singlet and triplet states. In parentheses, we have the production rate per year of these states in the main colliders. We have high production rates for positronium and muonium. For singlet states, we also perform rapidity cuts for production at the Born level, considering central and forward rapidities. Even with the cuts, we have high cross-sections, which allows future experimental measurements. We estimate high-order QED corrections, the so-called Coulomb corrections, for the production of parapositronium in heavy nuclear collisions. The Coulomb correction given by equation 17 has obtained based on the Kotkins paper. It has no dependency on rapidity, so it shifts the distribution at the Born level down equally at all points. We see the graph that its contribution is expressive and therefore it should not be disregarded. Our results show high production rates for parapositronium and paramuonium, so experimental analysis is possible. We also show that the Coulomb corrections for parapositronium production in 2 heavy ions collisions should not be neglected. I leave here our thanks for these funding agencies. These were the references used in this work. Thank you for the attention.